You're listening to Worth Electronics What's Up Radio podcast, and each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who will shine a light on interesting topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. Developers of switch mode power supplies face the challenge of developing their circuit to be EMC compliant. Conducted interference occurs in the input circuit whereby other electrical equipment can be disrupted. Therefore, the conducted interferences are first checked at the beginning of an EMC test of power supplies. The developer can already perform measurements during the development phase to get an impression of possible interference. In today's podcast, we discuss the procedure for examining differential mode interference in the input circuit of DC to DC switching regulators. First, we need to discuss the cause and development of the interference voltage. A distinction has to be made between differential and common mode interference for conducted interference. The triangular input current of the switching regulator is the active current and initially pure differential mode interference. However, this differential mode interference can actually transform into common mode interference in the case of unsymmetrical supply lines and results in increased electromagnetic radiation over the supply lines. The differential mode interference can be connected to ground using parasitic capacities and results in common mode interferences. In our attached figure 1 in this podcast, we see the typical input current of a DC to DC switching regulator with a pulse frequency of 2 megahertz. The input current flows with the pulse frequency of the switching regulator and resembles the coil current flowing through the storage inductance of the switching regulator. The AC component of the input current, which is approximately 260 milliamps in this example, is decisive for the differential mode interference. It's imperative to minimize this using an input filter. Due to parasitic effects of supply lines and components in the input circuit, high-frequency oscillations in the megahertz range occur during the rise and fall of the input current. The input current via the ESR of the input capacitor and the impedances of the supply lines of the switching regulator results in voltage drop, the so-called interference voltage. It must not pass the supply lines of the power supply, and it needs to be suppressed to a minimum. The unwanted AC component at the input capacitor of the switching regulator can be determined using measurement with an oscilloscope. This measurement enables a first statement about the interference voltage. In our example, there is an electrolytic capacitor with unknown but relatively high ESR, which causes a peak-to-peak value of the unwanted AC component of approximately 2.8 volts. Oscillations in the high-frequency range caused by parasitic effects are also present. In this example, the frequency of this oscillation is approximately 71 megahertz. Next, we'll discuss the test setup for the interference voltage measurement. Already accompanying the development, the measurement of the interference voltage of differential mode interference can be performed using a LISN, or a line impedance stabilization network, and a spectrum analyzer. The circuit ground forms the reference potential in this test setup. This defined test setup allows us to perform reproducible measurements and generates defined impedance both for the spectrum analyzer as well as for the switching regulator. In attached figure 2, you see the internal design of the DC LISN according to CISPR 25. The CISPR 25 is used as the basis for testing vehicle electrical systems, and it can be used for EMC testing, accompanying development of DC to DC switching regulators. The function of the LISN is decoupling of the interference voltage as pure alternating quantity V sub diff. It is measured using the internal 1 kiloohm resistance. The internal low-pass filter of the LISN prevents interference with other electrical equipment connected to the supply network. The voltage source V sub sup is connected to the input terminals of the LISN. The test item, in this case the switching regulator, is connected to the output terminals and also supplied with a voltage, V sub DC to DC. Attached figure 3 shows the result of a peak value measurement of the interference voltage with a spectrum analyzer. As a test item, a DC to DC step-down or buck converter without input filter was examined with a switching frequency of 2 MHz, input voltage of 10 volts, and input effective current of 0.7 amps. The interference voltage is determined in different frequency ranges depending on the standardization. So in this example, the measurement was performed according to the test regulation CISPR 25 with start frequency of 150 kHz and stop frequency of 108 MHz. The basic oscillation corresponding to the switching frequency is clearly visible. The harmonics reaching into the high megahertz range drop in amplitude. The amplitude of the basic oscillation is at its greatest with 128 decibels microvolt. The interference level, or V sub diff, can be defined in this equation, which is V sub diff equals 20 log times V sub ripple divided by 1 microvolt multiplied by decibels microvolt. So if this equation is transformed, the measured interference voltage, or V sub ripple, can be determined as V sub ripple equals 10 times V sub diff over 20 multiplied by 1 microvolt, which equals 10 times 128 over 20 multiplied by 1 microvolt. Using this, we get a value for the interference voltage, again, our V sub ripple, of 2.6 volts. This approximately corresponds to the peak-to-peak value of the previously measured voltage at the input capacitor. An input filter is obviously required. For example, the CISPR 24 Class 1 defines a limit value of the peak value of 66 decibels microvolt for narrow band interference and a frequency of 2.0 megahertz. However, the limit values, according to CISPR 25 and other standards, are not applicable for such measurements accompanying the development, as the measurement of the differential mode interference is not defined in the EMC standards. However, they can be included to make a rough assessment of the interference emission in power supplies. The worst case is usually considered to be able to determine the maximum interference emission. Therefore, the measurements for switching regulators are performed at full load and smallest input voltage. In order to illustrate this, the same test item, in contrast to the first measurement, was loaded with a load current of only 50 milliamps. Our attached figure 4 shows that the interference emission at low load is lower in the high frequency range. In this case, the basic oscillation shows a value of 112 decibels microvolt, and in comparison with a full load is only 16 decibels lower, however, not negligible. Next, we'll discuss detectors for assessment of the interference voltage. If the test item is tested in an EMC test accredited laboratory, the common mode interferences are measured in relation to ground. According to the standard, then not the peak value, but the quasi and average peak values are measured. These display modes are usually selected for assessment of measurements of the common mode interferences. Many high-quality spectrum analyzers also have quasi and average peak detectors. The measured interference voltage is conducted via the input attenuator to the band filter and then overlaid in the mixer with an intermediate frequency of an oscillator. The mixed product is amplified in the intermediate frequency amplifier and then fed to the detector. The display mode to be assessed of the interference voltage is selected at the output of the detector. In the average peak detector, the amplified intermediate frequency voltage is first rectified by a diode, which charges the storage capacitor to the current value of the envelope curve. The resistor is used for the later discharge of the capacitor. Afterwards, the voltage of the envelope curve is smoothed via the low pass from resistor and capacitor, so that finally the arithmetic mean, the average peak, is set at the capacitor. This display mode is selected because modulated carrier frequencies, as occur with switching regulators, can be displayed and assessed using it. In the case of the quasi-peak detector, similarly to the average peak detector, a storage capacitor is charged. The intermediate frequency voltage is first rectified via the diode. Afterwards, the storage capacitor is charged with a time constant via the load resistor. The storage capacitor can then be discharged using the time constant. The display of the spectrum analyzer, here the measuring instrument, then shows the average value of the charge and discharge pulses of the storage capacitor as quasi-peak. In this display mode, the electrical value of the interference voltage is converted to a display, which corresponds to the interference impression of the human ear and is received, for example, during radio reception as crackle interference. In summary, we discussed the necessity of accompanying EMC measurements on switch mode power supplies during development. An oscilloscope can already make an important statement in advance about EMC interference at the input of the switching regulator. However, measurement of the interference voltage with a spectrum analyzer and a listen are still needed. If an input filter is already taken into account during the development phase of switching regulators, the filter effect can be checked in the development laboratory using a simple spectrum analyzer. By using this method, the developer can determine unwanted interference levels at the switching regulator. With the selective use of filter elements, the developer can ensure that their application passes the final EMC test. Attached images are available in most podcast streaming networks. To view all images, visit www.we-online.com/podcast. To download the complete application note discussed today, visit Worth Electronic online at we-online.com/appnotes. You're listening to Worth Electronics What's Up Radio Podcast, where each week we are seeing what's up in the world of electronics and PCB design. We're checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up Podcast.